All right, well, good Wednesday morning. Welcome to another fun-filled day of calculus. The plan today, of course, after we have a chance to go over homeworks, I want to show you a little bit more about separable differential equations because they're actually pretty easy to deal with. But we'll do that, and then we'll spend some time reviewing for the exam that's on Friday, right? So hopefully you guys saw the message about the exam in terms of what it covers. Excuse me. Um, so it's primarily chapter 2 and then the first few sections of chapter 3. So we'll talk a little bit about those topics after we get done looking at separable differential equations. All right. So with that, are there homework questions you guys would like to look at? I imagine probably not many because there's no homework due tonight, and you're probably thinking more about the quizzes. All right. Okay. Well, with that, then let me go ahead and switch over to the other board, and we'll just dive into some differential equations. So I'll be right back.
Hey Bruce, I know you said 3.7 won't be on the exam, but if we have time, like I know people want to review the quiz
Here
more.
first. So I'm sorry,
Oh,
I didn't hear any of that because I was in the process of changing my
oh,
audio.
sorry.
So I just
I
saw
was
your
gonna
message.
say I had a 3.7 question, but if you want to do the quiz review, I think that would be more. I mean, not quiz review, just test review for Friday's exam. That would be more helpful. But if we have time, can we do
No,
number?
we can definitely do it. I got time. So let me go ahead and pull that up and we'll go take a look at it.
All right, thank you so much.
Yeah, you're welcome. Alrighty. Okay, so from 3.7 and reviewing improper integrals is not terrible for this exam anyway, seeing this exam is all about integration. Can you remind me again what number that was, Susanna? 13?
13.
Okay. All right. So Laplace transform of a continuous function of an interval is defined by this, where we're going to integrate from 0 to infinity e to the minus sx times f of x dx. This definition is used to solve some important initial value problems in differential equations. Domain of f is the set of all real numbers s such that the improper integral converges. All right, so blah, 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 Laplace transform, blah. Don't worry about what the Laplace transform does or what it's useful for, although it's useful for initial value problems. Yeah, okay. So you will learn about Laplace transforms a lot when you take differential equations. But for right now, this is just a, hey, let's use this as a reason or as an application of the indefinite integrals. Okay, so let's go ahead and set this up. We've got a function of 2, so we're going to put that in for f of x, and then we're going to integrate. So let me switch to a whiteboard. All right, so what we've got, we're going to integrate from 0 to infinity e to the minus s times x times 2 dx. Right, so we're just putting in our function 2. So we want to integrate this thing. All right, so let's think about this improper integral. So the s is just it's a constant. It's just, we don't know what it is. So it's a constant variable. So when it comes to integrating, we treat that like a constant. Obviously, the issue is the infinity, because e, regardless of what kind of powers and stuff we've got there, e to something times x is going to be continuous, so we don't have to worry about vertical asymptotes or anything like that. So this is only like that first type of improper integral. So let's go ahead and turn this then into a limit as a goes to infinity. The integral from 0 to a of 2e to the minus sx. And let's do this integral. So luckily, this integral is pretty quick. The 2, of course, stays there. So this one would be a u substitution. So we'll go ahead and work it out here. So we have u equals minus sx. So du would be minus s dx. So the dx would be du over minus s. So we're going to integrate from 0 to a e to the u over negative s. And then that's now a du. All right, so how are we doing so far? We're all...
I think I just overcomplicated this with the limit.
Yeah, possibly.
Like the a part.
All right, so
it's just a placeholder, right?
Yeah.
Okay.
Yeah, and it's going to get replaced with the infinity. So we've got minus 2 over s. The integral of e to the u, of course, is e to the u. Right? But we need to substitute back in our u, because remember, those are x bounds. So let me bring it up here. So we have minus 2 over s times e to the minus sx, evaluated from 0 to a. Oh, I dropped my limit. Remember, there's the limit out here. All right, so this is then minus 2 over s times e to the minus sa minus e to the 0. So we got the limit as a goes to infinity of minus 2 over s times e to the minus sa minus 1. So now let's think about what happens as a goes to infinity.
It becomes exponentially negative.
So we have e to the very, very negative number, which is 1 over e to the very positive number. So 1 over something really, really big goes to 0. Right?
Uh-huh.
So again, think of e to the minus sa, the same as 1 over e to the positive sa. So that's 1 over something incredibly large goes to 0.
So I'm just left with 1.
Yep. So you get minus 1. So the minus 1 times minus 2 over s becomes a positive
2 over
s.
Yeah. Oh,
so,
s. Oh, it looked like a 5.
Yeah, I know.
Okay.
Luckily,
thank you.
We don't have any 5s in here as well. But yeah, so that's the Laplace transform of the function 2. For whatever good that does for you right now. Yeah, but there it is. It's 2 over s.
I think I just had never heard of the term. Like, I think that was like a French.
Yeah,
term. It's whatever it was called.
It's the name of a French mathematician who came up with the idea. So, but yeah, what you're gonna see when you take differential equations, because I mean all of you are gonna take differential equations, right? If you take differential equations, you'll learn about Laplace transforms as a way of solving initial value problems. So remember, we were just talking about differential equations. There were general solutions and particular solutions. the particular solutions come from solving an initial value problem. Well, Laplace transforms are a way of doing that, of finding particular solutions, solving initial value problems, that basically turn it from calculus to algebra. It just becomes an algebra problem. And you know how us mathematicians like to go back to algebra because it's quote unquote easy. That's what Laplace transforms are all about. So anyway, but good question, and thanks for sharing that with me. Are there any others before I hop back up to the whiteboard? All right, this time for realsies. I'll see you up at the other screen in just 1 second. All right. Okay, so last time we were talking about differential equations, and the whole idea of a differential equation is it's got a derivative in it. And we saw that for certain types, we already knew how to solve them, right? Like the ones where we have y prime equals a function of x. That's just integration. We know what to do there. We also have y prime equals ky. We'd seen that one before, where function's rate of change was proportional to its quantity. And that led to exponential. But that really pushes us towards this other form. That's what we call separable. All right, so that's what we're going to look at here today. All right, so separable differential equations. So these are ones that can be written, so through algebra. So through algebra, we can get the form where we have some function of y times dy equals some other function of x times dx. So whatever this ends up looking like, the f of y and g of x, it's just all of our y's are on one side and all of our x's are on the other side. And once we get here, when we get to this form, then all you have to do is you just integrate both sides. Because integrating is going to get rid of your differentials. And we're going to have now something that's just in terms of y and x. Okay, so this is what it means for it to be separable. You just have to be able to manipulate it so that the variables are on opposite sides. So an example was the one that led to exponentials. So we've seen this where we've got y prime equals k times y. And the manipulation that turns it into what we see up here, we start by making this a dy dx. And then you can just divide by y, multiply by a dx. So we get dy over y equals k times dx. So this was a separable. And in fact, I think I showed you this last time, how that leads to our good old PERT formula, CE to the kx, or however you want to think about it. But you can see this now. We've got f of y times dy. It's 1 over y times dy. And then g of x dx, well, it's k times dx. But we were able to do what we wanted, which was get all the variables separated. We are ready to go. All right, so really, this is going to turn into an algebra problem where we just have to get ourselves so that all of the letters are on one side separate.
Bruce, I think you accidentally muted yourself.
All right. So a differential equation is separable if it can be written as, if you have y prime equals, I'll call them big F and big G. Excuse me. So if you can take your differential equation and actually write it when it's y prime equals, if you can see that as a product of two functions, one that's a function of y, the other that's a function of x, then you know it's separable. All right, so like if you come back to this one, the y prime equals k times y, you can see it. Here's a function of y. There's a function of x. They're being multiplied together. That tells me I can separate it. All right, so they're not that hard to notice or to spot in many circumstances. Like, for example, let's say we have y prime equals y times, say, 3 minus x squared. Here it's clear as day. I've got functions of y, and I've got functions of x that are being multiplied together. Y times 3 minus x squared. This next one, it may not be quite as easy to see. But like, let's say we have y prime equals x over y. This is, again, a function of y times a function of x. And I know you're probably looking at it going, that's not times, that's divide. But don't forget that division is the same as multiplying, right? That's 1 over y times x. So the same thing actually holds here where I wrote it as multiplication. If you want, think of it as division. And that's still just as good. So if you have a function of x divided by a function of y or vice versa, that's still going to be one that's separable. All right, but then you get ones that look like this. And these are the tough ones because you don't immediately recognize that they're a function of x times a function of y. Let's say you've got this 2xy plus y prime equals x. Okay, so here's a differential equation. Now this one is separable. Start by writing it as y prime equals. So we get y prime equals x minus 2xy. And like I said, this one's a little tricky because you look at that and you don't see multiplication. You see subtraction. And unlike the division, where division really is multiplication, addition and subtraction is not. But does anybody see how we could manipulate this algebraically to create it as a function of x times a function of y? It's the dreaded F word.
Factor out the
yeah, we can factor it out. You factor out an x, since there's an x in common, and you see that we get y prime equals x times 1 minus 2y, and now you can see it, hopefully. Right, we've got a function of x times a function of y, 1 minus 2y. So that's another way that you can recognize that you have separable, because it's one of those things where you don't want to try to separate it if you can't. You don't want to spend the time trying to do the algebra to move everything to one side or the other when it's not possible. All right, but this is one way you can tell. Just look and see, do we have these two functions that are being multiplied together? One that's a function of the one variable and one that's a function of the other, right? Obviously, I'm using y and x, but it's the same if it's y and t or p and t or p and q or whatever the hell they are, right? As long as you can split it into the two, this is going to be separable. All right, so let's just practice solving them, and we'll actually solve the ones that I've already got on the board, right? Just so you can kind of see how they work, and they're not that terrible. It's just a question of what do we end up getting. So let's look at this guy here first. The y prime equals y times 3 minus x squared. So we'll go ahead and go all the way and we'll solve this thing. So we know that it's separable because we can see that it's a product of the two. So let's just do our algebra. The y prime is a dy dx. So I'm going to split that first. Now I'm going to multiply by dx to bring that up here, and I'm going to divide by y. So we'll get dy over y equals 3 minus x squared times dx. So there's the separation. Right? There's the move all the letters that are y's to one side, all the x's to the other side. Real quick, it's super important, super important in terms of how you're going to manipulate and move around, that you have your differentials on top. Don't ever divide by a differential. Okay, the little dy's, the dx's, you want those things on top so that when we integrate, we're in the correct form. Okay, so don't ever try to solve this as get y over dy. That's going to be a problem. Leave it as dy over y. All right, so now that they're separated, we're going to go ahead and integrate. So the 1 over y dy, that gives us a natural log of y. So we've got natural log of y. On the other side, we're going to get 3x minus x cubed over 3. And then we need to put in a plus c. And last time, I don't think anybody asked me about this, and I'm a little surprised, actually. You notice how I didn't put plus c on both sides? I don't know if anybody was thinking about that back in the day, and they're like, why aren't there a plus c on both sides? We never do. We never put a plus c on both sides, because suppose I had a different, let's not call it c, but let's call it d, that I added on this side. It's just an arbitrary constant that I could move over by algebra. All right, so then on this side, I'm subtracting two arbitrary constants. That's just in itself another arbitrary constant. So it's totally legit to just put your plus c on one side. And in fact, it can be either side. We tend not to put it on the side with y, since we're trying to solve for y. And it's just going to add to an algebra step that we don't need. So we tend to put it on the other side. All right, but you only need the one. All right, well, now it's time to solve for y. Since this is natural log of y, that leads to an e. So we're going to get y is equal to e to the 3x minus x cubed over 3 plus c. And then the other trick that we always pull is if you got a plus c as an exponent, we actually turn that into a c out front as a multiple. Okay. So what the hell about that one? All right, so that's the rules of exponents, that when you add exponents, it's the same as multiplying. So since we had this plus c, It's really the same as having e to the 3x minus x cubed over 3 times e to the c. And the same kind of argument can be made there as the subtracting of two arbitrary coefficients. If c is an arbitrary coefficient, e to the c is also arbitrary. And we end up just calling it c again because, well, we're lazy and we don't want to use all the letters and all that sort of stuff. If it makes you feel any better, we could call it, say, C1, where C1 is equal to e to the c. That's really where that's coming from. But again, lazy mathematicians, yeah, we're just going to call that C. All right, so you wouldn't be wrong if you left it like the second step, right? If you had, now, I don't want to speak for the computer. I can't speak for what the computer is going to tell you is right or wrong. But I'll tell you, like on an exam with me, if you were to write that, I'm going to give you full points. Even though it's more standard to see it written this way. Okay, so they're both fine. They're both correct. They're just different form. All right, but check it out. We did it. Remember, solving a differential equation is all about figuring out what is the y. Well, we got it. We have the function whose derivative is equal to 3 minus x squared times itself. And we're able to do it because it was separable. All right, so there's that one. Let's do the next one and make it an initial value problem where we actually know something about the function so that we can figure out what the c actually equals. All right, so let's try this. This is the second one that I had written up as an example of a differential equation that's separable. Right, so we're going to have y prime equals x over y. But again, we're going to make it an initial value problem. Let's say that what we know about the function is that at 0, the function is equal to 1. So that right there is an initial condition that's going to let us find c. All right, so let's again start by separating. So this is dy dx equals x over y. So we get y dy equals x dx. All right, so it's separated. Now let's integrate. So the integral of y, of course, is y squared over 2. The integral of x is x squared over 2, but again, we're going to put on a plus c. All right, so let's get our plus c. Let's figure out what that c is equal by using the initial condition. So we know that when x is 0, y is 1. So the initial condition means that 1 squared over 2 is going to equal 0 squared over 2 plus c. So we're substituting in for both x and y. And this one, since I didn't actually have it as y equals, that's fine. I can just plug in at this point. And in fact, you can see that we're still going to be able to get c, right? This tells us that c is equal to 1/2. So we can put that back in. And what we've got then is that y squared over 2 equals x squared over 2 plus 1/2. And at this point, we can solve for y. So I kind of ran out of space. Let me bring this over here. So I multiply everything by 2. I get y squared equals x squared plus 1. And then I can just take the square root. And I get y is equal to the square root of x squared plus 1. So there is the function whose derivative is x over y. Now, I need to talk about two things with this one before we go really away from it. Well, I need to talk about one thing. I want to talk about another. First of all, the need to. When I went from y squared equals square plus 1 to y equals the square root of x squared plus 1, anybody see in there what the issue is with that, or the potential issue?
You're pretty much cutting the domain in half.
Okay, yeah, it's that whole plus or minus thing, right? I think that's what you mean by cutting the domain in half, right?
Yes.
I hope. Because that's what I was gonna go with. I mean, we've lost half of the values for y, right? When you take a square root, it's technically plus or minus. So there should have been a plus or minus in here. That's one that we often forget, but can be a major, major issue, right? So when I went and I did that, what I have to be really careful about is knowing, well, which one am I on? Am I using the positive or am I using the negative? And the way that I knew that it was the positive was my initial condition. Initially, my y was a positive 1. The only way I'm going to get positive 1 from a plus or minus is with the plus. So when you're in a situation like this, where you're going to do this extra step to go to get to y, be really, really careful, because sometimes that algebra leads to the plus or minus kind of issue. And when that happens, you have to make sure you pick the correct one, and your initial value will tell you. So because of that, mathematicians will often leave it in a form like this, where we don't actually solve for y, but we just go, well, this is the solution. It's y squared equals x squared plus 1, which is a perfectly fine equation. It's just not a function anymore. This is actually, if you were to graph it, it's a hyperbola. And you probably can envision in your mind hyperbolas, right? The things with the two branches. That those are not functions. They fail the vertical line test. And that's why we can't solve for y specifically. But when we're given an initial condition, we actually can solve for y specifically. We just have to watch out for it. All right, so that was the what we needed to talk about, because that's something that can show up and can cause a problem. But here's what I wanted to show you is how you can check. Because again, it's always nice to be able to check. Well, here's what you can do. If we think that the solution, and it seems like it is, right? Our algebra seemed like it worked, is y equals the square root of x squared plus 1. Let's check it against this by taking its derivative. So if we take the derivative of this, remember that this is to the 1/2 power. So we're going to get 1/2 times x squared plus 1 to the minus 1/2 times 2x from the chain rule. The half and the 2 cancel, and we're left with x over x squared plus 1 to the 1/2. So it's x over the square root of x squared plus 1. Okay, we'll come back to our differential equation. Remember, what we were looking for was y prime equaling x over y. Well, we got the x. And you can see how the bottom is actually the y. Let's just go back to the original, right? And so we can see that that actually is y prime equals x over y. So the good news with differential equations is that you can always check and see if you're correct, always, just by differentiating and doing the algebra on the form. All right, so this is the process. What you're going to actually have to do, like these get difficult when the integration is hard, or there's a lot of algebra that gets to that has to happen before we separate. You know, like with that one that I showed you where we had to factor out the x. But beyond that, let's just move stuff around and then integrate both sides. All right, well, let me show you real quick an application or two of these, just so you can see how they're used or where they're used. So I think what I'm going to do is I'm just going to show you two applications. I'm not going to go all the way through both of them, but I just want you to see how they lead to separable. All right. So here's the first type of problem that can be solved with separable differential equations. And this is, you've probably heard of it, Newton's law of cooling. And Newton's law of cooling is exactly what it sounds like. It's a law that talks about how objects cool when you take a hot object and you put it into a cooler temperature. It explains how the temperature changes. And it basically works like this. Newton's law of cooling says that the change in the temperature, or the rate of change in the temperature, so we'll be really boring here, but the rate of change of the temperature of an object is proportional to the difference in the temperature of the object and the environment. So the greater the temperature difference, the faster the temperature is going to change. And this should kind of make sense. I mean, so suppose you've got your hot cup of coffee, right? So you're drinking your coffee this morning. Your coffee, of course, is a little bit warmer than room temperature. Room temperature is going to be around 20 degrees, plus or minus Celsius. And then your cup of coffee, even if it's still boiling, like it's going to be at 100. So your coffee, when it comes out of the coffee pot, is probably not 100. Let's just say it's like 80. So there's a pretty big temperature differential. And what's going to happen is that coffee is going to cool off faster. It's going to lose degrees a lot faster than if it was close to 20. Right? If your coffee's like 23 degrees, so it's, you know, lukewarm at best, it's not going to change much because it's almost in what we call thermal equilibrium. All right, so it kind of makes sense that the rate of change in that temperature should depend on the actual temperature differential between the object and the environment. Okay, so this is what Newton came up with as his probably at the time radical idea. But it's definitely how this plays out. But let's see how differential equation works here. So first of all, notice it starts with the rate of change in the temperature. All right, well, hey, that's a T prime if I've ever heard one. We got the rate of change in temperature is proportional to, so proportional to, we're going to do K times the difference in the temperature of the object and the environment. So I'm going to put here in parentheses T minus, and I'm going to put another T here, and I apologize, but I'm going to have another T here. But I'm going to write T sub A. The T sub A, this is the environment's temperature. The reason I use A is for the word ambient. So ambient temperature, that's the temperature of the environment that we're in. Now that guy, the TA, that's fixed. Well, we're assuming that it's fixed. Obviously in the real world, even like room temperature can fluctuate up and down and all that. But we're just gonna assume, all right, we got our cup of coffee sitting here on the table, that the air around it is staying in the same temperature. Let's not get into the physics of really what's going on because we don't want to complicate the math. This is a good approximation. All right, so in terms of this, so that T, this TA, that's a constant. K is a constant, that's a proportionality constant. And so if you look at this and think of it instead of Y's and X's, think of it as, say, big T's and X's, you can see that this is separable. It's actually going to be really fast to take this equation and separate it. So let's do that. So the T prime, I'm going to rewrite that as dt dt. So we're going to have a big T for temperature and a little t for time. Okay, so those are the things that are changing. Our temperature is changing with time. So that's equal to K times T minus TA. And if I do just a little touch of algebra, barely anything, it's divide that by that factor and multiply by the little dt, we're here. So we've been able to separate. It was that easy. So now we'll integrate both sides. So on the left, we get a natural log. Right? And on the other side, we get KT plus C. And there you go. Now we've got it. So if you had information about your cup of coffee, like, oh, I don't know, the temperature it was originally, for example, you could plug that in for your T, for your temperature versus the ambient temperature, right? You can solve for your C, and the next thing you know, you're going to get a formula for the temperature of your object. So I'm going to just jump to the punchline because I know you guys don't care about the algebra. But if you do some algebra on this, what you end up getting is that T, it's equal to, so this is going to be the temperature of your, say, cup of coffee. It's going to equal T naught minus TA. T naught is your initial temperature, times e to the KT. And then we're going to add to that TA. So you do some algebra and you're going to get here. So obviously the ambient temperature matters, right? What's the temperature of our environment? That's why there's this plus TA. And we're going to have T naught minus TA. So clearly it depends how hot what the original differential in the temperature was. And then we get this e to the kt. Now the k is going to change. It's going to vary. But that guy, I'm going to put here, it depends. The value of k is going to depend on some things. Really, it's going to depend on the object itself and how well it conducts temperature. Right? So does it lose its temperature fast versus slow? For example, like aluminum versus steel. Right? Steel takes longer to heat up. So it's going to have a different K value than aluminum versus water versus, whatever. So Bruno, you just said, so in essence, we're turning these into exponentials. Well, this time, this one turned exponential because of the fact that we only had a t over here. We had a 1 over t, which led to a natural log. It really depends in terms of just like in general, how our equation separates, what it looks like when we've got the variables on either side. So it will lead to exponentials a lot, but it will also lead to other things. Like think about the example I did just before this that gave us a square root, right? So you never really know what you're going to get until you separate it and integrate. But if when you separate, you get a dy over y or some form like that, it will be exponential. So, all right. Anyway, so
chime in
yeah,
possibly just to say the dorkiest thing that maybe any of us are thinking, which is, wow, Newton's such a badass. Like he came up with like calculus and thermodynamics and like theories of gravity and some stuff about light too. Like, awesome.
Yeah, just some stuff about light. Yeah, no, Newton was pretty incredible, dude. He was also really strange, like really strange. For example, the light, the optics stuff. He would, because he recognized like the lensness of our eyes and all that. So he was like fiddling around with his eyes. He would experiment on himself. He would like jam a spoon into his eye and then kind of like tweak it around to see what kind of differences it would create in his vision and stuff like that. There's a story, he invited somebody over for dinner and of course was like in his own mind doing whatever math. The guest came, was waiting for Newton, finally decided, okay, well, I'm going to eat. The food's already out on the table. Newton comes in. It's like, oh, I see we've already eaten, and turns around and walks away. Like, yeah, crazy cat, but pretty incredible. So I'm definitely with you. There's a reason that lots of things are called Newton. Did he make an equation for a spoon on the eye? Not that I know of. Not that I know of. All right, so here's an example of where you use separable. I think I'm actually not going to show you another one for the sake of time. I want to spend some time reviewing for the exam. But like there are all kinds like mixture problems. Suppose like you've got a here's something that would lead to a separable differential equation. Suppose that you've got a pond, freshwater pond, and then some pollutant starts coming in from some source. If you wanted to figure out what kind of pollutant, like you wanted to describe the pollutant level over time of that pond, that would lead to a separable differential equation. You want to talk about this thing falling through the air, right? In basic physics, we just go, oh, the only thing affecting it is gravity. But then you go, yeah, but in reality, there's air resistance, there's drag. Well, when you put in drag, it leads to differential equations. And again, that's one that can be separated, right? So there are all sorts of situations where you get separable differential equations or differential equations on their own. And we'll see more of those as we go. Anyway, all right, so I'm going to hop back down to my computer so we can chat a little bit more about this exam and some of the things you should be able to do. All right, so I'll be right back. Alrighty. So differential equations are cool. And I know that you're all totally excited and thrilled about what we were just doing. But you're probably thinking more about this thing that's going to happen on Friday and what you should know. So let's talk a little bit about that, just to kind of refresh your memory and the kinds of things that you need to know how to do. All right. So first of all, let's just kind of tackle most recent first. So the stuff from chapter 3 are all the integration techniques. All right. So 3.1 through, what did I say was, I think 3.4. So that's integration by parts. That was 3.1. 3.2 was trig integrals, being able to do with like the sines and the cosines and things like that. 3.3 was trig substitution. So that was the one when we had the difference or sums of squares, and we could substitute in with the sines or tangents or things like that. So that was 3.3. And then 3.4 was the partial fraction decomposition. Okay, so that's as far as we're going to go in terms of chapter 3, but those are definitely things you should be able to do. So when you see an integral, be able to recognize what techniques do I need to use. I am going to want to see all of your work on these things, all of it, right? Because I know that there are resources that you can just punch it in and get an answer, both online and in hand. So I'm going to be a stickler on these. If you don't show me your steps for your integration, or if you just go to the, oh, I've set up my partial fractions and then it leads to magically a equals 1, b is 1/3, right? Just don't do that. Show me where it's coming from. Anyway, so know how to do those different kinds of integrals. So for example, just to practice a couple here, what if I gave you, say, this one? Let me go ahead and share my screen again. Let's go to a whiteboard. But suppose this was on your exam and I said, all right, I want you to integrate tangent to the 4th. So what are we going to do? What's the approach for this one? So what do you immediately think? Think about our different integration techniques. Which one pops up in your head?
Is it the 1/3 one? Like
the 1/3 one. I don't know what you mean by that.
You break the fourth, the power. You break the power basically.
Okay.
You differentiate the power, so it goes 1/3.
Okay.
And that way we have less to integrate.
Okay, I gotcha. All right, so yeah, so this is the one where we do want to split it apart, right? And I think that's kind of what you're getting at, Susanna, with the breaking it.
Yeah,
down.
sorry, I don't know how to explain it well.
No, I'm with you now. But yeah, so this is a trig integral, right? And so we have some options. One thing we can always do is turn them into sines and cosines. So you can make this like sine to the 4th over cosine to the 4th. That'd be totally fine. Or since it's tangent, maybe we want to do tangents and secants, right? So that would be an option as well. Okay, so the question is, which of those do we want to do? Well, here's my recommendation. My recommendation with this one actually would be to break it into sines and cosines, because with tangents and secants, remember what you need. We're always looking for having the derivative of those trig functions as part of this integral. So like with, say, tangent, its derivative is secant squared. I don't have those. The derivative of secant is secant tangent. I don't have that. But if I were to break this into sines and cosines, so this is sine over cosine, I totally have what I need to do these integrals. right? So this would be one option. The other thing we could do is, since I've got tangents, but I want secants as well, so I'm gonna kind of do this as two different possible routes. We could say, let's do this as tangent squared times tangent squared. And I know that tangent squared from the Pythagorean identity is equal to secant squared minus 1. And so I could rewrite this as tangent squared times secant squared minus 1. That should be there. Right? And so now I'm starting to introduce secants as well. And so you kind of have a couple of different approaches for how you can try to do this. Either way, you're going to be making use of identities. All right, so what do you guys think? Which path here might be better? Thoughts, ideas? Having horrible flashbacks? All right, so I got a vote from Alexi for the tangent. From Bruno, got sines and cosines.
Actually, Bruce, I don't know if it's a third option. What about what Susanna was talking about? Because I remember there was a video in the homework that tells you to, it's like that word formula of tan to the n minus 1 over n minus 1 minus the integral of tan to the n minus 2. I know that
I
was
think
kind
yours
of,
is similar enough. It's similar. It's not the.
Okay, so that formula.
You would get the same answer.
Yeah, that formula is what comes about from doing this.
okay, that's
Because
what I thought. Yeah.
Yeah, if we were to continue with this one, so like this is now
Turns
tangent
into
squared.
by parts, right?
Yeah, secant squared minus tangent squared. So remember how you were saying, so you get that thing with the 1/3 blah, 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 minus the integral of tangent squared. Well, there's that integral of tangent squared. It's coming from that guy right there. So this is actually what leads to that magical formula that was in the book. And there are a bunch of those that I don't want to call them power reductions, because those are specifically terms we use for identities. But for integrals, there are definitely patterns that spill out if you do them generically. And so you'll see in calculus books all the time generic formulas for things like that have patterns. So the one that you're specifically talking about, I'm going to see, I'm going to go to the book and pull it up for you guys, because I know roughly where it is.
Oh, I only brought it up because I thought it would be easier just to integrate tangent once, like to the power of like 1, then to the power of 4. But your way also seems to be just as much work, so.
Yeah, it's gonna get you to the same place here. Let me just share it real quick because I've got it. And I didn't talk about it, but it's this guy right here, number 3, I think is the one you were talking about, right?
Yeah.
Where you get so tangent to the k is actually the same as tangent to the k minus 2 times blah, blah, blah. So you get here. And that's exactly what I was doing. If you think about, I've got now my tangent squared times secant squared minus tangent to the 0. Or wait a minute, that should be, no, oh yeah, minus tangent, integral tangent squared. Yeah, so tangent squared secant squared minus tangent squared. And then I like how it says you may need to repeat this process on the tangent squared term. And yeah, you would. Sometimes you're going to have to repeat this. But then you can always get down to integration by parts. So I think, yeah, here's a good example with the tangent to the 6 secant to the 4th. And so they're like, all right, so use this little formula. and then it can turn into this guy, right? Here's the other, your reduction formula. So here's your generic, what it looks like, right? But again, where that's coming from is making use of the identities. So if you don't remember the formulas, that's fine. You don't have to know the formulas. You can just go to keep doing the identities to get to your integration by parts. So if you were to do that exact same thing with ours, let's come back to the one that we were looking at. And obviously this exam, you've got all your resources, so feel free to use the formulas, that's fine, right? Just make sure you tell me I'm using the reduction formula or whatever. Explain where you're coming from.
I think sometimes I put it on like the margin of my test. I put the formula I'm using, like the generic one.
Yeah.
So
No.
that's okay. That's okay, right? If I were to do that on the test, but I just leave the generic formula on the sides written somewhere.
Yeah, because then really the idea is you want to make sure I understand what you're doing, right? And if you have got that, I'll recognize that as, oh, she's using the reduction formula, blah blah blah. But yeah, that's totally cool.
And then I had another question.
Okay.
Sorry.
No, that's all right. Go ahead.
Okay. If I were to use like a U sub, not on this problem exactly. I mean, even though we could do U sub, do you want us to write the du, dv, and v, or can we just put the u?
Yeah,
like
I want to see it.
If we're running short on time,
I want to see it all.
Okay.
I want to see it all.
Got it. Thank you.
Yeah. And we'll actually do that on this piece right here. All right, so we've got, if we kind of use that formula that we saw, or how this is going to play out. So this is going to become 1/3 tangent cubed. And that comes from the fact that the derivative of the tangent is a secant squared, right? So at this point, you would let u equal tangent of x. So du is secant squared. So this thing is the integral of u squared du, right? So you get 1/3 u cubed. That's that piece. But then for this other one, we're going to need to do integration by parts. So let's think about how we're going to break that down. For integration by parts, probably want to let u equal tangent squared. So then dv is going to be dx. Du will be 2 tangent times secant squared. And v is going to equal x. Oh, we don't want to do it that way. Because I'm already seeing that when we go have to do our integral of v du, that's going to be a problem. Oh, I know what I would do.
Yeah, I would say, wouldn't it turn into 1 minus secant squared? Or 1, yeah, secant squared minus 1.
Yeah.
Can we convert the tangent squared integral to secant squared minus 1 using the I don't know. I don't know if I'm going to help.
So Susanna, I'm going to say yes because I just said yes to that, because that's exactly what I think that was Adam said. So, oh good Lord. Okay, so yes, I can do that. So this would be the same as the integral of secant squared minus 1. Right, and then so then,
but we get back tangent.
So secant, yeah, so then the secant squared, of course, we know that that one gives us a tangent. So we get 1/3 tangent cubed minus tangent, not tangent squared. And then plus x, because the minus minus is a plus. All right, so there would be the integral of tangent to the fourth. Regardless, when you've got these powers, remember that it always depends on even, odd exponents, which one's got which, and we kind of go from there. Okay, so there would be, say, the integral of tangent to the fourth. There would be a process that gets us there. And it's really just using identities, and u sub gets us to where we need to be. All right, so how about, here's another one for review. What if we wanted to integrate, say, sinh times cosh squared? So let me clear some space here on the whiteboard, and let's try this again. So again, let's say we're going to integrate sinh times cosh squared. All right, so looking at that one, what technique comes to mind?
You mean like u sub or?
Okay, so you like u sub?
Yeah, I would.
All right, I think that's also a great idea. Be careful with the hyperbolics. When you see the hyperbolics, you might think trig, but remember, these guys are not trig. They are different. They are different functions. But yeah, this is one where we definitely want to do a u sub. And in fact, cosh and sinh are beautiful, because regardless of which one you've got, the derivative is the other. You don't have to worry about plus or minus signs anymore. So this one, if we did it this way, we let u equal cosh, then du is going to equal sinh. So this is actually a nice and easy u squared du, which of course would give us u cubed over 3, which would be cosh cubed over 3 plus c. All right, so don't, even if it might look kind of ugly and nasty, don't fall for it. Because sometimes, even though they look big, ugly, and nasty, they can be done very quickly with u sub. So kind of u sub is one of my go-tos when I want to do an integral. It's the very first thing I think about is, can I do a u sub? Because if I can, then it's going to be much faster and much easier.
Yeah, that's funny, Bruce. I went the complete opposite way though. I used u for sinh, and it made this ugly where you had to add the quantity to the other side and then divide by 2, and
that's gonna suck, man. Why'd you
I don't know, because I wanted to waste time, I guess.
Yeah. So okay, so that actually brings up a good point. How do, like, obviously when I went here, I just wrote u equals cosh, and I didn't talk about how I chose that. But why did I choose cosh over sinh? Well, now this sort of is kind of the same idea as before with the patterns. What I saw was that whichever one I pick, the other one's going to be part of my du. And I recognize that if I pick cosh, then the du is going to have the one and only sinh. And so that's going to go away. Where if I had picked sinh for my u, the du would have had one of these coshes, but still another cosh remaining. So it really is, and this sucks to hear as a student learning integration from someone who's been doing it for decades. It really is pattern recognition. It's the fact I've done a million u subs, and I've seen, like, I've gone down those paths, like you're talking about, Adam, where you go, I chose the wrong one and it got ugly and horrible and nasty, right? I've done that enough that I can see it coming. I think about that. It'd be like, all right, you get into a bad accident going too fast on a curvy road when it's wet. And you start recognizing, oh, there's a curve coming up. The road is slick. I need to slow down. because I've been through that experience, I know what to look for. So yeah, if you choose differently, that can be pretty gnarly. All right, so that's a good integral to think about. Okay, so what about this one? What if we went with this integral? We'll make this a definite integral. Let's go 0 to 1, and let's look at, say, x over e to the 2x dx. No, let's make these t's. We haven't done any with t's. All right, so let's say we've got this integral. Now, the fact that it's got bounds, whatever. But yeah, this one's definitely going to be an integrate by parts, as Bruno just put in the chat. Because if you think about this, remember, integration by parts works really well when you have multiplication. I just want to show you that this is multiplication, right? Dividing is the same as multiplying. We can think of it as multiplying by the negative power. So this is one where you definitely want to use parts. So let's remember our little mnemonic device, liate. So in terms of the pieces, we've got an exponential and we've got an algebraic. So the algebraic is what we're going to want to use for our u. So we'll let u equal t. So then dv is going to be e to the minus 2t dt. So du is dt. V, the integral of this, is going to be a minus 1/2 e to the minus 2t. That one comes from u substitution. So integration by parts, we have u times v, so minus 1/2 t e to the minus 2t, minus the integral of v du, so that's going to become a plus 1/2 integral of e to the minus 2t dt. So it was a plus because of the minus minus. I pulled a half out for it. But this is one of those where we saw integration by parts sometimes needs, you know, another integral kind of deal. This one, at least we don't have to do parts again. That's another just u sub. So that's going to be a minus 1/4 e to the minus 2t. And now we take care of the bounds. So we don't worry about the bounds at all until the end anyway. So do your integration by parts, do the repeated integrals, you know, do as many as you need, then put in your bounds. So let's see, what does this give us? Minus 1/2 e to the minus 2t minus 1, or minus 2, minus 1/4 e to the minus 2. That's plugging in the 1. Plugging in the 0, I'm going to get 0 from this piece. And this one's going to be a minus 1/4. All right, it's whatever that is once we distribute and group. All right, so what led us to see parts here is recognizing that it's multiplication, and also that we don't have other tricks that are going to help. Obviously, this isn't a trig or a trig sub, clearly not a partial fractions, but there's that guy. All right, so my best advice when it comes to the integration is look at the form, practice the form. And probably better to practice not by going to a specific section in the book, because if you go to the section on trig substitution, you already know, yeah, this one's coming from trig substitution. Better to maybe go to the end of the chapter and find random problems that just say integrate, so you can practice recognizing what forms to use. Right. The ones that have been a little bit more recent, I'm not going to like go through these all the way, but just to kind of remind you things to look for when it comes to the other forms, right? What is it that leads to trig substitution? What form are you looking for? What kind of thing shows up in an integral that tells you, ooh, try trig sub? Okay, so square roots are often part of it.
Parentheses.
Not always, but yeah, there's usually some sort of grouping. And so then Alexi's getting at where I want to go.
Together or subtracted from one another.
Yeah, so what you're looking for is either a sum or difference, right? So we're either adding or subtracting squares. Okay, so that's the big thing. Look for sum or difference of squares. That's going to lead to trig sub, or that's where trig sub can work. It's not always what we want, but that's the kind of thing that's going to work, or make trig sub work. So we did see a lot of them that were like inside of square roots, but they don't have to be. I mean, you could still do a trig sub if you had just plain old x squared plus a squared, right? But any of these forms, x squared minus a squared, x squared plus a squared, or a squared minus x squared, that's the trigger for trig sub. All right, that's the pattern that when you see that, you go, ooh, you use trig sub. Right, and then partial fractions is pretty clear too. If you're going to try partial fractions, that's got to be when you've got a rational function, right? So that you can actually start by breaking it apart. So my advice when it comes to, here's the question that just says integrate, break it down and just start looking at, okay, is it a fraction? Nope. Okay. Yes. Partial fractions, right? You can kind of make your little schematic or your the flow chart, right? Is it a fraction? Yes. Try partial fractions. No. All right. Does it have a different sum or difference of squares? Yes. Try trig sub. No. Move over. Right. Okay. Then does it have just trig functions? Try trig integration. If nothing else, it does have multiplication. Let's try integration by parts, right? So just get good at practicing and seeing what the form is. Just don't forget some of the easy things, right? Like U substitution can sometimes knock out these problems much faster than the other forms, even though they'll still get to the same place, right? You can save yourself some time. So what I do personally is I just do a real quick mental check of U sub. I look and see, is there a decent U sub that's going to help me out? If not, then I go to the whichever form or whichever technique the specific form tells me to do. All right, so that was, I mean, that's your real quick recap of the integration part. So that was the chapter 3 stuff. So chapter 2, that's all the applications. So let's kind of talk about things to remember from chapter 2 that you're going to need to be able to do. And so the first one was volumes by shells, because I am pretty sure that where the last test left off was at volumes by slicing. So remember how to do volumes by shells. Volumes by shells, that's where we're integrating 2 pi r h, because this is the volume of the shell. 2 pi r is the circumference, h is the height, so that's our cylinder, and then we multiply by our little tiny thickness. Just some things to remember with that. If you are rotating about the y, you're going to use dx, because the dx and the dy, that's the thickness of the shells. And so if we're rotating about a vertical axis, our shell is going to have horizontal thickness. And the same thing if we're not rotating about the y-axis, the axis there, it's the same thing is true for any vertical line. If you rotate around any vertical line, you're still going to use your dx's. You just have to change your radius accordingly. And then the same deal if you're going to rotate about the x-axis, you're going to use dy for your thickness. So I know it's been a while. That's why I wanted to kind of bring that back to remind you. This is a big fact when it comes to doing volume by shells. So my recommendation there is draw the picture, draw a representative shell so you can figure out what the radius is, how to determine the height. The height is usually either from the function or the difference in functions, right? Because we usually have the top of our shape and the bottom of our shape that we're spinning around. So that usually comes from the difference of functions. And then the R, that's either the X or the Y, again, depending upon which way you're going. Just remember to adjust it accordingly if you are rotating about a different axis. All right. Anyway, so volume by shells, that's a total blast from the past if you go back to 2.3. But as we continued in the application, we still did some more geometric stuff. So in addition to volume by shells, remember how to do arc length. And arc length is actually really easy because it was the integral of the square root of 1 plus, and I'm just going to put here y prime squared dx. But if you got your function as y equals, take its derivative, fire it into this, and you integrate from wherever your lengths are. So the big kicker on this was you didn't have to have it as y equals. It could have been x equals. And then you do x prime and dy. It's exactly the same just because of the format. Oh, so here's fun fact. When we did arc length back in the day, you may remember that we got to these integrals and I told you, oh, these integrals are horrible and nasty, and most of them we can't do right now. Just use your calculator. We can do them now. What technique are you going to use for arc length? Quite possibly.
Trig substitution.
Hey, trig sub, because we've got a sum of squares. And even better, which trig sub? Which one do you use for sum of squares? Do you remember which function you use? That's the one, it's tangent. So a lot of arc length integrals actually do use the tangent trig sub. So, hey, fun fact. Okay, so that's arc length, and then also with arc length was surface area. And with surface area, you're integrating 2 pi RL. So it looks a lot like the formula for shells because it's really coming from the same place. So in terms of the L, you're going to use your arc length bit. You're just going to use the correct form either with the dy or the dx. And then you get your radius, and the radius is going to be from your function as well. So arc length and surface area were very related to each other, and another geometric application. So that one, probably the best idea for both of these sections, again, is just to go back and set some up. Go through the process of, all right, so here's an example that they gave us of find the arc length, and get your integral set up. Maybe don't spend the time going all the way through the integral unless you want to practice your integration techniques, but at least practice getting them set up because that's most of the battle with the geometric thing. Okay, so we did geometric stuff. And then after the geometric stuff, we went to the physics applications. So let's kind of talk about all the different kinds of physics applications that we had. So what do you remember? What physics applications did we do? Okay, so good. So Alexi, we have mass. So we can find mass. What else? Work, good. All right. So volumes, Bruno, I'm going to say we kind of already did. We kind of lumped that into geometry, although it does apply to physics. But we did have fluid forces, right? That came from pressure. I'm going to put one more on here. Center of mass. So these were really the big things that we did with the physics. We looked at how to calculate mass, work, fluid forces, and centers of mass. So to kind of remind you how those work, let's do this guy. Hold on a second here. Too many windows open, as always. Okay, so let's say we are given a rod that's got a density of x plus e to the minus x. Let's find the mass. If it goes from x equals 0 to x equals 3. All right, so it's a 3 meter long rod. So we're going from 0 to 3, but we've got this as its density. So calculating mass from density is really easy. All it is the integral of your density function. So this one would be the integral from 0 to 3 of x plus e to the minus x dx. So at this point, you're going to actually kind of like a problem like this one. Well, depending upon what that density function actually looks like. But it's really easy to set it up because all you do is you just integrate the density. Right? So like this one, if we were to finish this off, let's see, it gives us x squared over 2 minus e to the minus x at 0 and 3, so it's 9 halves minus e to the minus 3 plus 1, I think is what you get when you do the 0. So this would be how heavy or how much mass this rod actually has. So that's a pretty quick one to do. When it comes to work, the big thing for work is that we're integrating force times displacement. And sometimes it's the force that's variable. Sometimes it's the displacement that's variable. So depending upon how we want to build this out, the little dx chunks or dy chunks or whatever that is, sometimes it comes from the distance that we're moving, and sometimes it comes from the force. Examples where it can be one or the other. When we did those ones where we were, say, moving the water out of a tank, that one, the little dx came in the force because we were looking at the weight of a little tiny slice. Other times it was in our displacement. An example of that would be like when we were, lifting a box to the top of the building. There it was our displacement that had the dx because the box had constant force. So as an example of one of those to kind of remind you how that worked, let's say we've got a 100-foot long cable that weighs 200 pounds. And then that cable is holding a 50-pound box on the bottom. And the question is, how much work would we have to do to pull it all the way up? All right, so you kind of remember problems like that, I hope. So let's get that guy set up. Let me clear something. And now we can do it right here. Okay, so we've got a 100-foot long rope or cable that weighs 200 pounds. And it's lifting a 50-pound box. The question is, how much work does it take to lift it up? So it doesn't actually matter how tall the building is or anything because we're just pulling up the 100 feet of cable. And the idea with this one would be to split it into two pieces. Think about the box and the cable separately. So if we think about the box, it's got constant weight. And what it's doing is it's moving up here. So we're going to break this down into a little differential motion or differential portion. Okay, so let's just think about moving that little distance. In that little distance, its force is 50. The displacement is dx. And so we're going to do that the entire length of the cable, which is going from 0 to 100. So here's the part that's going to be the work done to pull the box up. So this is an example where the dx is part of our displacement. But that's because we have constant force. It's constant weight. All right, so that's that piece. I'll let you figure out what that number actually is. Right, 50x over 2, so 25x, 2,500 foot-pounds, I think, is what that piece is. Okay, so now let's look at the cable. So to think about the cable, again, let's break it down into a little differential chunk of cable. Okay, so we're just going to look at this piece. So in terms of how far it's going to move, it's going to have to go up a distance of x, depending upon where we are. But now we need to get its weight. Well, its weight is going to be its density. Let me not use W because we'll think of that as work when we just write it out. So the weight is equal to density times length. So if we just think about this little differential chunk, it's got length dx. Its density comes from this right here. If it's 100 feet long and it weighs 200 pounds, then its density is 2 pounds per foot. So for this one, we're going to integrate 2 dx. Oh, sorry, that's the force. But then we have to multiply by its displacement, how far it's moving, which is x. So that piece, we're going to have an integral from 0 to 100 of 2 dx times x. So it was its density times its little length chunk times the distance it's traveling, which is x feet. So it really depends on what type of work we're doing, which kind of version we're looking at, how we want to get those things set up. Okay, so there's an example of how to do the work problem. Again, you can go ahead and do that. It's going to be x squared, evaluated 0 and 100, and then you would add them together. Okay, so there's that guy. So let's talk real quick about fluid forces. Let me clear these guys. And an example of fluid force, remember those good old like windows and dams and things like that. So let's say we've got this guy. Let's say we've got a circular porthole that's underwater, and let's say that it's got radius of 1 meter, and it's located so that the top is just at the very edge of the water. And we want to find out how much force is acting on this, or how much force. So in terms of finding fluid forces, does anybody remember what the general formula is for fluid force? So we're going to integrate And it's going to be, yeah, thanks, Alexi. It's pressure times area. And the pressure, we get pressure by looking at density times gravity times depth. So the trick with these is to go with things that are constant depth. So let's look at a piece here that's at constant depth. Assume that's all at the same depth. What we want to do is we want to figure out its area so we can multiply by its pressure that it's feeling. So the trick to these is all about finding the cross-sectional area. That's the area of the little chunk. All right, so we can pick our 0 to be wherever we want. It doesn't really matter. But to help us actually get this cross-sectional area, we're going to turn to triangles. So let's say that this is the center of the circle. I've got a little right triangle that looks like that. This side is the radius. This one, let's just go ahead and call it x, because I know the area of that little slice, it's going to be 2x times dy, because its length is, because of the symmetry, it's 2 of those, so 2 x's, and then its thickness is dy. But what I'd really love to do is get x in terms of y. So here's what I'm going to do. I'm going to make this side be y. So that I've got x squared plus y squared equals r squared. Or x is the square root of 1 minus y squared. So that makes my area 2 square roots of 1 minus y squared times dy, which means my force is going to be the integral. We'll worry about the bounds here in a second. But I need rho times g. Okay, so those are going to be constants, times its depth. Okay, so to get the depth, though, the way I've got mine set up, I've got my y equals 0 is through the center. So the depth of this slice is right there. And that depth is going to be 1 minus y. Because remember, the radius was 1. If I take away my y, that gives me my depth. All right, so my pressure is rho times g times my depth, and then times my cross-sectional area. So 2 square roots of 1 minus y squared dy. And notice that this is now all in terms of y. The rho is constant. If this is fresh water, it's 1,000. If it's salt water, it's 1033 or whatever. Gravity, of course, is 9.8 meters per second. The 2 is a constant. So all that's constant. The rest of it is integral with respect to y. The last thing I need to worry about are my bounds of y, though. So the way that I've got it set, if y is going right through the center, I need to drop the radius and go up the radius. So these are going to be integrals from -1 to 1. So this would be the integral if we set up our center at 0. You can, of course, adjust it to have your y equals 0 be anywhere. Just in general, it's easier if you put it at the center of the circle.
I have a question about that really fast.
Yeah, go for it.
So I just remember doing this one, and then so from the area, I thought we did like the area of the circle, so it's like pi r squared, so it would just be pi. Is that not how you would find the area?
No, this one, when we say area, this is a cross section of area, and I'm going to put here at the same depth. And that's really the kicker to this, is you want to do it at the same depth, because everything at the same depth has the same pressure. Because if we were just to look at the area of the circle as a whole, the parts on top are feeling less pressure than the parts on the bottom. And so it's not going to play out for us. If we had constant pressure over the disk, that would be fine. So this would be like, let's say that porthole was sideways. So it was flat. Then you want to find that pressure, or that one, then you would multiply by the area of the circle, because that entire circle is at the same depth. Does that make sense? Kind of seeing where I'm going there.
And then if you put like the y-axis at the top of it, like it could be like 0 and 2, like it's going, like if you do know how we did it in the
Yep.
note.
Yeah, so again, depending on how you choose your 0, if you had chosen your 0 to be at the top,
Yeah.
and then going down, then yes, your bounds would have been from 0 to 2. Your depth would have been y, right? Because the slice is going to be y down. But your cross section would be different. We'd have to change this because it's no longer the square root of 1 minus y squared. So you'd have to change your picture a little bit. Instead of this being y, because y is now your depth, this would actually be 1 minus y, right? Because now the little red arrow here is y. So if I want to get this length, that's 1 minus y. So that would change this to x squared plus 1 minus y quantity squared equals r squared. So instead, this would be the square root of 1 minus y squared. So you notice that it has pretty much the same form, just the details have changed because we changed where 0 happens to be.
Okay, thank you. I think I did like, I didn't do the area right, but I did the other stuff right then.
Okay. But yeah, so here's the thing. You have infinite choice of where you make your 0. So by how you pick your 0, it's going to kind of drive everything else. Why I chose to go at the center is, again, I've done so many of these in my lifetime that I know going from the center of a circle is a little bit easier in terms of formulating cross-sectional area. But that's personal preference. All right, so hopefully that's kind of a good reminder of how to do the fluid stuff. And I see that we're like way over time, but let me just really quickly mention about the centers of mass. Centers of mass, you really are doing kind of the same idea as finding mass itself, but just remember that when you find the center of mass, say x bar, it's actually my divided by the mass. My is your moment about the y-axis, which is all about your mass times your distance away. And there are formulas for finding the mx and the my. The mass, you're going to do exactly what you do with that first example I showed you with the rod that had the density. You just integrate. But the mx and the my, make sure you use those formulas, which are either y times your little mass chunk or x times your mass chunk, depending upon which one you're doing, and then integrate over the entire length. So anyway, that was the last of the physics applications. But then I do want to point out that there were a couple more sections, just to be nice and complete here. After we did all the physics applications, a couple more things you should know are the exponential growth and decay. But hopefully you remember that that was pretty quick and easy. And then the other last thing was the hyperbolics.
So just some things about both of these real quick. So exponential growth decay, know how to do them, know how to set them up and find them. They're pretty straightforward. The hyperbolics, I know there's a ton to remember in there in terms of the derivatives and integrals and the inverse hyperbolics, all that. Again, feel free to make use of your notes, your textbook, whatever, to have all those formulas. And it's totally fine that if I say, hey, I want you to say differentiate the inverse tangent of x or something like that, right? It's totally fine to go and say, all right, I know that the formula for the inverse tangent derivative is this and all that. So I wouldn't bother trying to remember all of them. Just be able to use them and realize that you still do the same thing with chain rule and product rule and integration by parts and all that. They're just another set of functions that we can use when we're, that we can use, period. Whew. Okay, so there's a lot that's going to be on this test, right? Or a lot that's possible. But really it breaks down to, I would say, two big chunks. There's the do the integrals, and there's the do the applications, right? So we got integrals and applications. So there are going to be quite a few quote unquote word problems because those are all the different applications. But realize that I'm going to be cool. I'm not going to give you like, 3 fluid force problems that require all this. No, I'll give you one. Like you can pretty much write this test right now, right? There's going to be a fluid pressure, fluid force question. There's going to be a work question. There's going to be a volume question. There's going to be either a arc length or surface area question. There may be a center of mass question, right? Yeah, probably a center of mass question because then that takes care of the mass one as well. So there's your applicate. Oh, and then some sort of a exponentially loggy kind of question. All right, so there's your application. And then in terms of integrals, expect there's going to be a partial fraction, a trig sub, and integration by parts. All right, so there's 9 of the questions, and it's usually about 10 or so questions long. So there you go. There's the exam with just a little bit of variation. Oh, so we'll throw it hyperbolics. There you go. That'll be our 10th question. But there you go.
To clarify, can I ask a question?
Of course.
Okay, you said after this exam, if we like our grade as it is, we can skip your final, right? Or in the beginning of the semester, quarter. You said something about the final. If we take it, it may or may not increase.
So I'm buying time to try to remember because that was a long time ago. So I'm going to tell you, Susanna, what I would do to answer this question is I'm going to look at the syllabus and I'm going to see what I said about that on the syllabus.
Okay.
Because I don't remember, but because
if you do all the homework assignments with a 50% grade or better.
Okay, because what I was going to say is it depends in which class I'm teaching, what little nugget I give people. So, but it's always based on, yes, you have to do all the homework, at least half 50% score on each one. Then you get the bonus special thing. And if in this class you don't have to take the final exam, if that's what I put on the syllabus, then that's what it is.
I have a question about that too. Are we going to have grades for everything in those so that we can decide by then?
Yep, you will. That, Lexi, that's like a couple of weeks away, right? Still 2 more weeks. I'll get stuff up and in. There's not a lot that's withstanding, right? That's outstanding. I will have stuff. I know you like having it right away, and I know a lot of you had Larry, who's the king of, oh, you took it, I'm going to grade it within 5 minutes. I am not that guy, right? But I will get them in. Don't worry. You will definitely know what your grade is well before the final. Yes, I know Larry grades it as you take it. But Larry's a whole nother creature. He's a completely different guy than me. So, as I'm sure you've figured out now after a couple months.
Hey Bruce, do we have to tell you that we're like when we make our decision, or when?
Yeah. How about we worry about the final when we get a little closer to the final?
Okay. Yeah.
I don't mind. I don't mind the questions. It's just I haven't really thought about when I need to hear from you guys and all that, so I don't have answers. And I think right now it's probably more important for you to worry about the thing that's next, because the final is later, right? Let's tackle the next thing next. All right. But we'll definitely talk about the final next week in terms of how everything's going to be set up and all that, because we still have all of next week. We also have a week from Monday as a class day, so we still have quite a bit of time together. All right, so before the final. Anyway, so how about this? Any other questions about the upcoming exam? Are you guys feeling pretty good about what to expect? I'm not saying, are you feeling good about the topics, like being able to do it, but you know what to expect? All right, so it's the same deal as always. There's not going to be class. It's just going to be taking the test. It's going to be turning on at 8:30 on Friday morning, and you'll have until the usual time to turn it in, which I don't really remember. But again, consult the consult the syllabus. I think it's 11:10. Does that sound right? 11 o'clock, something like that. But anyway, you should have plenty of time to do it. Just make sure you show me your work. Don't give me just magical miracle answers. All right. Okay, so I'm going to go ahead and stop class then, and wish you all a good luck on the test, and I will see you all on Monday.